Today we talk about logarithms. Logarithmic functions. And I'm going to turn this down. All right, tell me if I'm not loud enough, tell me if I'm not clear enough. Here we go. We're going to talk about inverting exponentials. We're going to define the logarithm. We're going to talk about properties of it. We're going to talk about interpreting the logarithm, graphing the logarithm, and using the logarithm. Recall that when we talked about function inverses, we talked about two motivating examples. Well, we talked about a few, but here's two of them. Exponential growth. So for instance, when does a population reach a certain size? So for instance, when is my bacterial culture ready? And exponential decay. For example, in radioactive decay, how long did it take for the parent isotope to reduce to this amount? Okay, how old is my sample? Okay, and to answer those kinds of inverse questions, we need to invert the exponential. Okay? And that's why we're going to talk about the logarithm. And incidentally, you guys are, the people who are in biology at least, are going to come across, I'm sure the physics people too, the people in biology are going to come across logarithms at least a few times. I showed you a log-log graph in here. Log-log graphs make power laws look like straight lines. You'll see semi-log graphs, okay, which make exponential laws look like straight lines. You come across this when you do column chromatography, when you do gel electrophoresis, when you do spectrophotometry, you'll see it. So you'll see logarithms a lot, even if sometimes they're hidden from. Okay, so we need to talk about inverting the exponential. Good? Okay. So, is the exponential function b to the x, b greater than 0, b not equal to 1, invertible? Who says yes? Come on. Who says no? Equal, come on. Okay. Yes. Otherwise, this is going to be a very short lesson. Okay? If you've got b greater than 1, you've got exponential growth, looks like that. If you've got b between 0 and 1, you've got exponential decay that looks like that. Okay? Do those pass the horizontal line test? Yes. Wherever I draw a horizontal line, it crosses at most once, and same story here. Okay? These functions are one-to-one, therefore they're invertible. Okay? This one's increasing everywhere, this one's decreasing everywhere. And like we talked about before, if something has that property, yeah, it's invertible. Okay? Okay. And we ignore the stupid case b equals 1. We'll focus on b greater than 1. So the exponential growth case. Okay. So let's call this guy, actually. Okay, f at x equals b to the x, b greater than 1. Let's graph it. X, y. Okay, b greater than 1, so we have exponential growth. Passes through 0, 1. Good? And that's f. How do I get the graph of f inverse? Someone say something? Now say it again.
Flip over the horizontal axis.
Flip over this. Okay? So the line y equals x. Line y equals x. Okay? Reflect this across that to get the inverse, yeah? Okay. I could use another color. Okay. And that looks something like... And that's f inverse. roughly. Okay? We had a horizontal asymptote here. The inverse has a vertical asymptote here. Okay? We grow really quickly here. The inverse grows really slowly here. The function had a y-intercept of 1. Its inverse has an x-intercept of 1. Okay? Everything flips over. Good? Okay. F is increasing. Is F inverse increasing? Yes. Good. Okay? So both of them are increasing everywhere. Or I say everywhere, through their domains. What is the domain of the exponential? Good. Everything. Yeah, good. The reals and its range?
Y is greater than 0.
Good, yeah. Okay, the positive reals. Okay, so this guy, the domain and range flip with respect to this guy, okay? So the domain of this guy, domain of F inverse, is the positive reals, and the range of F inverse is the reals. Does that make sense? Okay, the domain of F inverse is everything to the right of this axis, and the range is everything. Okay? This does keep growing, there's no asymptote there. Okay? Good. Okay, and the inverse of the exponential function with base b is called the logarithmic function with base b. The logarithmic function with base b, and the definition is there. Okay, the logarithm with base b, I'll try again. The logarithm with base b, where b is greater than 0 and b is not equal to 1 of a positive number x is denoted log base b of x and defined by log base b of x is equal to y if and only if b to the y is equal to x. Okay, so in other words, the logarithm base b of a number is the exponent to which the base b has to be raised to give that number. Okay? And like the exponential, it's a transcendental function. Okay? So it's not algebraic, if you care. Okay? Questions? All right, example. Okay, log base 10 of 0.01. What is that? No, thank you. Good. Okay. Log base 10 of, what's this? This is 1 over 100. That's just 10 to the minus 2. Okay, and that says what exponent do I have to raise 10 to get that number? And the answer is obviously minus 2. Good?
Yeah, shortcuts.
Okay. What's the logarithm base 2 of negative 2?
Say again.
Wait.
The logarithm base 2 of negative 2. You're allowed to get upset here.
Is that possible? Yeah.
Good, yes, good. Bad me, right? No, exactly. Doesn't exist. Okay? We said the domain was the positives, that ain't positive, okay? There's no way to raise 2 to anything to get minus 2. Okay? Similarly, what? Log base 3 of 0. Okay? Same deal. There's no way of raising 3 to something to get 0. Okay? Okay. Logarithmic and exponential functions with the same base undo each other or cancel each other. Okay? They're inverses, they better undo each other. Okay? Log base b of b to the x is just x for any real x. And b to the log base b of x is equal to x for x positive. Okay, what am I saying? I'm saying that the exponent to which b must be raised to give b to the x is obviously x. And here we're saying if you raise b to the exponent required for b to be raised to give x, that gives you x. Okay? Hopefully in your brains that makes some kind of sense. Okay, basically they're inverses so they undo each other. Good? Like we talked about before. And like the cancellation equations before, you've got to be careful with the domains here, okay? For instance, the exponential here is happy with anything, so you can feed anything into here and make it make sense. The logarithm only takes positives, so don't be feeding negatives into here or 0 into here. And that's it. Okay? Again, we saw that before. Generally, this is for the special case of exponentials. Questions? Okay. Example. If we said solve for x in 10 to the x equals 450, what would you do? Questions, are we ready for that yet? Yeah, we are ready. Okay, yeah, go ahead.
Log both sides.
Yes, log both sides. And then something would come down, presumably, right? Is that what you're thinking, wherever you are?
What?
Oh man, blank faces. Who are you? Thank you, hi. Okay, yeah, log both sides and then the x comes down?
Yeah.
Yes, and because I haven't told you that yet, let's pretend you don't know that. And what you could do is you could just write that, okay, x is the exponent to which 10 has to be raised to give 450. So log base 10 of 450. You could do that, yeah? Is that fair?
Okay.
Same answer, yeah?
Yeah.
Yeah, okay. You're right, but I just didn't tell you that rule yet, so you don't know it.
Oh, okay.
That's all. You're right. Okay? And you punch that into a calculator and you figure that out. Okay? Or like he said, you take logs at both sides. Questions? Yeah, okay, that's one way. I'll do this. I'll show you the second way real quick. So log base 10 of both sides. And what would you do? Would you bring the x down and all that, or no?
Come down and down.
Okay, right, okay. The other way you could do this, without having to use that rule, is recognize that you're basically looking at that, and so they cancel and you just got an x here. And that works too, yeah? Yes?
If it's log base 10, do we still have to write 10?
No. Let's say no. Although in some places, log nothing means ln, so be careful. Yeah, seriously, be really careful what people mean when they say it to you, but I think whenever I've written log, I've meant log base 10. Okay? Yes, sir?
Questions about the graph. Why is the inverse log b?
Why is the inverse?
Log b.
It's the definition of log b. It's the inverse of the exponential. That's it. Cool? That's it? Okay. Okay, laws of logarithms. I imagine the majority of you have seen these before. Okay, well, I'll just read this. If b, x, and y are positive numbers, b is not 1, and r is a real number, then you have these guys. The log of a product is the sum of the logs. The log of a quotient is the difference of the logs. And the log of x raised to the exponent r, you bring the r down, and you get r log x. Okay? Okay, and if you're wondering where the heck any of this comes from, should I not have done that?
Yep. I had a question about it.
That's a shame, isn't it? I'll try it again, I promise. What was your question? Can you tell me now? Wherever you are? Yeah.
Is y equals 0 an asymptote in that graph?
Is y equals 0 now? For log?
Yeah.
For log, x equals 0. So the y-axis is an asymptote.
Sorry, yeah.
Yeah?
Y, X.
Yeah. Yeah, the y-axis, x equals 0 is an asymptote, yeah. Of log. Okay. Do I want to say this? Yes? Okay. You don't have to write this down, just so you can make some sense of this. If we let w equal log base b of x, I think. and z equal log base b of y. Okay, each of those guys has an exponential rule that's a partner of it, okay? So for instance, for rule 1, b to the w times b to the z is equal to b to the w plus z. Okay? That exponential rule translates directly to that logarithmic rule. Okay? So that's where all this stuff comes from. bw over bz, sorry, b to the w over b to the z is equal to b to the w minus z. Second guy. And b to the w to the r is equal to b r w. And that's all that's happening in that third one. Okay? Don't worry about that, I'm just telling you that's where all those things come from. Okay? They're essentially exactly the same as the exponential ones, except in logarithm land. Okay? Questions? Suppose you wanted log base b of x squared. You could write log base b of x times x. Use the first rule to rewrite that as log base b of x plus log base b of x. And that's just 2 log base b of x. I hope. Good? So the exponent came down in front, okay? Which is this rule. Okay? So for r an integer, you can get this from these two guys, okay? But this is also true for general real r. Does that make sense? Okay, so for the special case of r an integer, you can get this just using these two guys, but for general real r, this holds as well. Okay? Okay. The logarithmic function is not linear. Okay? Do not do this. Log base b of x plus y equals log base b of x plus log base b of y. Okay, please don't go thinking that's okay, okay? Those are the rules, that's not right, okay? For instance, log base b, for instance, log base b of 1 plus 1 is equal to the log, let's call this log 2, log base 2. Okay, the log base 2 of 1 plus 1 is the log base 2 of 2, which is just 1, but the log base 2 of 1 plus the log base 2 of 1, okay, that's 0, you just get 0. Those are very much not equal, okay? All right? So again, please don't go thinking that the log of a sum is the sum of the logs, okay? The truth is that the log of a product is the sum of the logs, yes.
And how would you solve log base b x?
Say it one more time. That plus thing?
Yeah.
Agony. You don't, essentially. Yeah, you don't. You don't have a rule for that. That's it. If you see an example, you can show me. But yeah, if you probably have to play with it in some way. Possibly it winds up looking like a product. Otherwise, yeah, there's no sum.
But like log 2 base 2 is equal to 1, right?
Yeah.
Okay, so that's right, but the bottom right there is wrong. The last
The
one.
bottom's right as well. I'm saying these two are not equal. I'm saying don't do this because you don't get equal things on both sides.
Oh, okay.
Okay? Or more fundamentally, don't do it because it's just not right. Yeah? Okay? Okay. Okay. Real quick example. This is the board I'm on. Okay, for example, of these laws, log base 2 of 3 minus log base 2 of 48. All right, both of those are ugly numbers, right? Both of those logs are ugly numbers, but we could use the rules and write log base 2 of 3 over 48. Okay, which I hope is 1 over 16. And 1 over 16 is 2 to the minus 4. Okay? And this says what exponent do you have to raise 2 to get 2 to the minus 4? Well, minus 4. Okay? Questions? All right. Was there anything else about the graph that I erased? You'll be pleased to know that on my notes there is a great big thing underlined and in capital letters saying, do not erase the graph. Okay. Logarithms let us compare quantities that can differ by multiple orders of magnitude. Okay, if you understand that, you don't have to write it. Okay, let's see how that works. Okay. If log base b of y is equal to log base b of x plus 1, what does that mean? That means that the exponent I had to raise b to get y is 1 more than the exponent I had to raise b to get x. Okay? So that means that y is b times x. Does that make some sense? Okay? Or you could raise b to both sides of this and get the same answer. Okay? Okay, so either think about it or put b to the this equals b to the this and you'll get this. Okay? So a difference in 1 in the logs corresponds to a factor of base difference in the quantities. Okay? Okay, and similarly, if log base b of y is equal to log base b of x plus some number n, then y is equal to b to the n times x. Okay? A difference of n in the logs translates to multiplying by b n times in the quantities. Okay? Okay, so you can see how variation in order of magnitude translates to just a possibly manageable sort of number here that tells you the difference between the logs. Okay, and we'll see examples of that in a second. Okay, for example, log base 10 of 450 is equal to log base 10. Okay, 450 is 4.5 times 100. Okay, we can break it up using that sum thing. Okay, the log base 10 of 100 is just 2. So you get log base 10 of 4.5 plus 2. Like that, okay? This guy is 2 orders of magnitude bigger than this guy, okay? It's 100 times bigger than this guy, okay? So the log is 2 bigger than this guy. Fair? Okay, so the log base 10 tells us about the order of magnitude of a positive number, okay? So roughly how many digits there are, right? The log base 10 of 450 is something between 2 and 3, because this thing has between, let's see, how do I put this? So if you put this in scientific notation, it'll be times 10 to the 2, right? That's what order of magnitude is. Does that make sense to people? Roughly how many digits? Plus, minus 1? Okay? Okay. We can express a ratio between quantities as a difference between their logarithms. Did this make sense to people? Yes, sir.
Can you just clarify?
This thing? Let me just say that if log base 10, let's say log base 10 of 1,000, right? The log base 10 of 1,000 is 3. And that makes sense, right? It's 1 followed by 3 zeros. So you want to say the order of magnitude of 1,000 is 3. Right? This is a general sort of that kind of thing, right? This is 100 times bigger than this. It's 2 orders of magnitude bigger than this, and that's what this 2 is. Does that make sense? So if you're 2 orders of magnitude bigger, then your log is going to be 2 bigger. Okay, and that goes back to this kind of thing. Okay? Yeah, don't freak out too much over that. Are we okay? Okay. That roughly is what we were talking about here, and I'll give you an example now. Okay. I can talk about pH, the Richter scale, or sound levels. Who cares?
pH.
Thank you. Okay. All right, example. pH of an aqueous solution, okay, or the potential of the hydrogen ion, is defined as negative log base 10 of, again, just an example, don't freak out. I imagine most of you don't write this bit. I write this bit to make this thing unitless so that I can take the log of it and not feel bad. Okay? Negative log base 10 of the proton concentration in the solution. Okay? Okay. And that's the same as saying that the proton concentration is equal to, bring the minus over, raise 10 to both of these, 10 to minus pH moles per liter. Okay? For example, household ammonia has pH 11.9, carbonated water has pH 3.9, 3.9. Okay? That means the hydrogen ion concentration here is 10 to the minus 11.9 moles per liter. And here is 10 to the minus 3.9 moles per liter. Yeah? Okay. So the proton concentration in carbonated water over the proton concentration in household ammonia is 10 to the minus 3.9 over 10 to the minus 11.9, which is 10 to the 8. Okay? We had a pH difference of 8. We had a pH difference of 8, and that translates to a proton concentration ratio of 10 to the 8. Okay? Okay? Which is what I was saying there. Okay? And unfortunately, because of this minus sign, the one with the lower pH is the more acidic one. Is the one with more protons. Okay? Good? Okay, notice these are freakish numbers, right? These are horrible numbers. If you tried to write them out, you'd be writing a load of zeros, whereas these are manageable numbers. And that's a nice thing. Okay? Yes?
So write that as like log of 3.9 over log of 11.9 equals 8.
Log of, I wouldn't divide logs. I wouldn't go log that over log that. Is that what you're saying? Yeah, I wouldn't do that. Log 10 of what? Of 3.9?
Yeah.
See, the thing is, inside the log, you should only be putting stuff like this. So you shouldn't be putting the pH inside the log. Does that make sense? Yeah, if you're still curious about that, let me know and I'll play with it in case there's something. Okay? Yes, sir.
Factory row like log base b x plus 1.
Yep.
So that's the plus 1 lower negative.
Is that what you meant?
Yeah.
Yeah, yeah.
Okay, so why did you write that as y equals bx?
Okay. This says that the exponent to which I have to raise b to get y is 1 more than the exponent to which I have to raise b to get x. And that just means that y is equal to b times x. And that's that. Or again, you could write b to the this equals b to the this. Use cancellation rules and exponentiation rules and you'll get this. Okay? Alright. Other logarithmic scales. The Richter scale for earthquake magnitudes, okay, is a logarithmic function of the vibration amplitude. Okay? Sound levels in decibels, okay, are a logarithmic function of the sound intensity. Okay? So this stuff turns up a lot for things that vary a lot in order of magnitude. Okay, so you can turn them into manageable numbers. Good? Okay. And if you want those examples, I wrote them so we can talk about them if you want. Alright. Return to the graph that I definitely did not erase. That's b to the x, y equals b to the x. Okay, that's y equals x, that's y equals b to the x, and that's y equals log base b to the of x. Okay, looks familiar? Okay. What do I want to say? Again, remember b to the 0 equals 1. Again, this is all b greater than 1. B to the 0 equals 1, so this guy has y-intercept 1. That's 1 as well. Log base b of 1 is equal to 0. So the log has x-intercept 1. Okay, and those are saying exactly the same thing. Okay, they came from each other. Okay, I told you this horizontal asymptote turns into this vertical asymptote. I told you that growing quickly here translates to growing slowly here. And that's that. Any questions about this or anything else? Oh, yes.
Could you just repeat what you said about the growing quickly and one saying?
Yes. Yeah. Okay, so we talked about exponentials grow fast, right? And eventually grow faster than any power function. Okay? On this side, this guy grows slowly, and eventually grows more slowly than any power function. Okay? They do opposite things, these two. Okay. Thank you. And there you go, there's some pictures. Okay, it's just this thing with different bases. Okay? And we talked about how as we increase the base away from 1, we get more extreme exponentials. You can sort of think of this the same way, okay? So look at those things and make sure they make some sense to you. Again, all the log graphs are obtained by reflecting the exponential graph. Okay. Now, as we just talked about, logarithmic functions are hideously slow, okay? They eventually grow more slowly than any power function with a positive exponent. And for example, they grow more slowly eventually than any root function. Okay, so they look a bit root-like, right? As you get past 1, they look a bit root-like. Okay, but they're very, very slow, and any root function will eventually beat them. Okay? So for example, the square root is always ahead of log base e of x, which we'll talk about shortly. The cube root falls behind, but eventually beats the log. Okay? And as you go further and further out, it'll beat it by more and more and more. Okay? Log is ludicrously slow. Okay? In the same way that exponential is ludicrously fast. Good? Natural logarithm function. Okay, we talked about the natural exponential function, e to the x, e being that really special number. And it's the preferred base of the exponentials. Okay, it has some special properties, makes life nice, in the same way that talking about trig functions and radians makes life nice. The inverse of the natural exponential function is the natural log function. ln, pronounced ln, of x. Okay? Which is exactly the same as log base e of x. Which is that guy there. Okay? If this is confusing to you, you can always rewrite it as this, okay? But this is nice and elegant and...
What's the equal sign?
I meant is identical to. They're the same function exactly. You can write just equal if you want. Okay? Okay. Okay, everything we said about logarithms applies to this because it's a logarithm function. Okay. Suppose this was the natural exponential function. We talked about how one special thing about it is that the slope here is exactly 1, right? So as I flip this guy over to get the ln function, the slope here is also going to be exactly 1. Okay? Just a happy fact. Okay. And just be advised again, sometimes when people write log, they mean natural log. Okay? Not here, but in some advanced sort of texts and papers and that kind of thing. Sometimes just saying log means log. But here, and on your calculators, for example, just writing log means the common log, log base 10. Okay? All right. Questions? Okay. All right, let's see if I have an aneurysm doing it this time. Find the domain of the function f defined by f at x equals log base 10 of 1 minus ln x. Okay? Make all the functions happy. Okay? To make this guy happy, okay, again, what's the domain of ln? Positives, right? Okay, so x better be positive. So x better be positive. Okay, you've also got to make this guy happy, so all of this stuff has to be positive. 1 minus ln x has to be positive. Okay, that's the same as 1 greater than ln x. Okay. What does that mean? Ln x less than 1, okay? Okay, suppose this is the natural log. Ln x less than 1. At 1, we're going to hit e, okay? Ln of e is 1. Okay? Okay, so if you've got x between 0 and e, so between 0 and e, then you're going to get the ln less than 1. Does that make some sense? Okay? Again, the ln of e is equal to 1. So to get the ln of x less than 1, you've got to get x less than e. Okay? And again, there were no inequality flips here because everything here was increasing. Okay? Ln and exponential are increasing functions. Okay? Ln and natural exponential are increasing functions. Okay? Look at a graph, write the inequality, do things to both sides, whatever helps you figure that out. Does that make sense? Okay, so what's the domain? X greater than 0, x less than e, so it's between 0 and e. Okay, the function only works between 0 and e, excluding both of them, which wind up being vertical asymptote. Okay? Questions? Again, if this doesn't make sense, just let me know, okay? You can always look at a graph, and you can always sketch a graph and figure this out, okay? All right. Change of base. Change of base. Okay, an exponential function, b to the x, can always be rewritten with base e. Can always rewrite, and again, I'm going to assume b is greater than 1, b to the x with any other base, in particular base e. Okay, because we like base e, so sometimes we want to convert to it. Okay, how do we do that? A couple of ways. I'll show you one way, and if this isn't satisfying, just ask me and I'll show you the other way. Okay, b to the x. Okay. Another way of writing b is e to the ln b. Okay, raise e to the exponent to which e has to be raised to get b, and that gives you b. Okay, cancellation effect. And that's just e x ln b. B to the x is equal to e to the x ln b. Okay, and now we got it in base e. Okay? And if you want another way of showing that, I can show you another way. Okay, you can convert bases between logarithms too. Log change of base. Okay. B to the log base b of x is equal to x for positive x. That's just the cancellation. Okay? If I take ln of both sides, okay, this puppy comes down. And I can write log base b of x is equal to ln x over ln b. Okay, so your calculator doesn't have a log base anything button usually, right? So you can just do this then. You can just use the ln to figure it out. Or you can use log base 10 to figure it out, or any other base. Okay? So you convert between bases and logs. And if you remember how we talked about how horizontal scaling of exponentials is the same as a change of base, that's what this guy is. And similarly over here, a vertical scaling of log is equivalent to a change of base. Okay? There was horizontal scaling of an exponential, here was vertical scaling of a log, and they both correspond to change of base. Okay, questions? Okay. All right, here we go. Drug clearance. Once a drug is injected into a patient's bloodstream, the amount of the drug remaining in the blood falls exponentially and is modeled by mass at time t is equal to m naught times e to the minus kt, where k and m naught are positive constants, and t represents time post-injection. A, how long does it take for the amount of the drug in the bloodstream to fall to half of its initial level? Okay? And if you're a more physicsy type person or a chemi type person, you might want to think of this as just radioactive decay, and we're looking for the half-life or something. Okay? And the reason I put that locus there is because there's an experiment in biology 477L where you inject a red dye into a locust, and that's why that cute guy is all red. And then you measure how much red dye is in there at intervals. But your measurements are confounded by the fact that this guy doesn't like red dye being inside him, and so he's quote-unquote peeing it out. Okay? And so that's sort of like this. It's exponentially getting rid of stuff, in the same way that this drug would be exponentially gotten rid of or absorbed or whatever. So that's why that picture's there. And also, I think he's cute. And he's mine. Or was briefly. Okay. So first question is, what is m naught here? Someone shout, whoa, hey! Early start. M naught is?
Initial amount.
Yeah, good, initial, yeah, exactly. So the initial mass or whatever, the amount. And you can find that by what? Subbing in t equals 0 into this thing, right? You sub in t equals 0, that's 0, that's 0, e to the 0 is 1, so this whole thing is m naught times 1, so just m naught. Okay, so m naught represents the initial amount of stuff. Okay, second question is, how can we tell that this thing is exponential decay and not growth or something else? Yeah, that minus sign there and the fact that that's positive. Okay? Good. So in general, when you see stuff that looks like this, a base, so a constant to a constant times, let's say, time, be able to tell if that's decay or growth, okay? And that'll depend on whether this guy is less than 1 or greater than 1, and whether this guy is positive or negative, okay? And if you want any help with that, just let me know. Okay, so anyway, bottom line, that guy's decay. Okay, so let's answer the question. Okay, so again, we said that we started with m naught. We want to see how long it takes for the amount to fall to half of its initial level. So how long does it take? So solve this. Solve mt equals 1/2 of its initial level. Good? Divide both sides by this positive thing. Okay, we can now take ln of both sides. Or we could just say that is the exponent to which e must be raised to give this. So ln of 1/2 is just minus kt. Okay? Again, that is the exponent to which e must be raised to give this, so ln of this is just minus kt. Or you can take logs of both sides, this guy comes down, you get ln of e equals 1, and you'll get the same thing. Okay? Okay, if you want to be really cool, you write this as minus ln 2. Okay, you get rid of the minus signs, you solve for t, and you wind up with ln 2 over k, which is something you might have seen before. Okay, so that's a half-life thing. Okay, how long does it take for it to drop to half of its initial level? And we talked about initial level, but so basically we talked about how long it takes for you to fall from here to half of that, here. Okay, so that's the time we just determined. But if you start here and see how long it takes for it to drop to half of that, that'll be the same amount of time. Okay, half-life doesn't change over time with an exponential function. Questions? Okay. All right. If k is 2 reciprocal hours and 1.5 milligrams of the drug remains in the blood 1 hour after injection, how much was initially injected? Okay. So m at 1 hour is 1.5 milligrams. So we've got 1.5 milligrams. We just plug in. And m naught we don't know. E to the minus. K is 2 hours reciprocal. And we're talking about 1 hour. Okay? Okay, the business on the right is just m naught e to the minus 2. Okay, so the answer is quite simply 1.5. And I suppose this is math if you're sharp enough, just you can put the units at the end, or you can put the units all the way through like in science. Yeah. Or 1.5 times e to the 2 milligrams, which is roughly 11.08 milligrams. Does that make sense? Questions? People are dangerously quiet. All good? Someone nodded. One person nodded. Yeah, thank you. Brilliant. Okay. Also, when you turn those guys over to a handle, and they're really cute, they kick around looking at you when you try to do the
Question.
Yes, ma'am.
Wouldn't you have to change it e to the power of 2 instead of e to the power of negative 2?
Yeah, like I said, you could go 1.5 times e to the 2. Is that what you're saying?
You divided by e to the negative 2.
Yeah, I divided by e to the negative 2. Instead, you could multiply through by e to the 2. Is that what you're saying? So instead of this, you could have written... I hope. Yeah, does that make sense or no? That's a no, isn't it?
Let's say it.
Broadly, does this make sense? Just see me if there's anything problematic, okay? All right.